Thank you so much. Dr. Gilder, thank you so much for the invitation. And Carver Mead, it is such a pleasure to see you here today. There's been a lot of talk today about AI and how much it's changing the world and what an economic impact it has, present day and in the future. I'm going to be addressing what appears to me to be a billion-dollar problem, perhaps a trillion-dollar problem, and one which requires a technology solution. So something consistent with George Gilder's original writings about microcosm, going deeper into the technology to find the solutions. Instead of going deeper into the silicon, this time it's going deeper into the neural architecture in order to find a solution to a billion or trillion-dollar problem. The problem is the hallucination problem. Everyone is aware that ChatGPT gives beautiful, fluid answers much of the time. However, some of the time it's disappointingly wrong. Those are called hallucinations. And I'm going to call on Andrej Karpathy, who gives a succinct statement of the problem and why it is currently unsolved. In some sense, hallucination is all that large language models do. They are dream machines. We direct their dreams with prompts. The prompts start the dream, and based on the LLM's hazy recollection of its training documents, most of the time the result goes someplace useful. It's only when the dreams go into deemed factually incorrect territory that we label it a hallucination. It looks like a bug, but it's just the LLM doing what it always does. The point of that is that hallucinations appear to be an inherent property of the LLM architecture. Now, you would think that the giant corporations with Google, Amazon, Microsoft, with enormously funded teams and incredibly talented people, you would think the problem would have been broken in the last year or two. But this is a statement from Sergey Brin, co-founder of Google, from only a few months ago. It's a problem right now, no question about it. We have made them hallucinate less and less over time, but I would definitely be excited to see a breakthrough that brings it to near zero. You know, we can't just count on breakthroughs. I think we're going to keep doing the incremental kinds of things we do just to bring the hallucinations down over time. But like I say, a breakthrough would be good. So even the big tech giants admit that they don't have a solution to this surprisingly thorny problem. This is a billion-dollar problem, depending on how you count it. If you count it based on the investments that have been made, it's a multi-billion-dollar problem. If you count it based on the market capitalizations of the companies whose logos are shown here, it's more like a trillion-dollar problem because their valuations are inflated because of the expectation that they will capture a big share of the market in the near future. That high market valuation, the trillions of dollars, depends on a solution to this technical problem, which they don't have. So that's setting up a bubble dynamic. Bubble could pop if they don't come up with a solution, I would say pretty soon. Okay, so it's a billion-dollar problem, maybe even a trillion-dollar problem. So now let's take a look at what is it about this architecture that makes Andrej Karpathy say it's inherent, you can't solve it. So I'm going to do a little brief description of what the architecture of a large language model is. This is the picture from the 2017 paper, Attention is All You Need, written by the researchers at Google. However, I'm just showing it here because some of the people in the audience may have read that paper and may be familiar with it. In fact, this is not a good description at all of what a large language model is. It's the original Transformer paper, but this is actually describing the technology that they invented in 2017 for machine translation. This is not a description of a large language model at all. So if you read the founding paper of the field, in fact, you would be misled into thinking that this was the architecture. This is a better picture of what a modern large language model actually looks like. Now, I'm not going to go through all the details of what's in it. I'm going to abstract this into a simpler form. This picture is, in fact, all that I need for the discussion today. Namely, most of the fancy machinery here, the 70 billion parameters, are in the layers between the embeddings of the pink layer at the bottom and the green softmax at the top. All of that stuff is the transformer, this advanced technology that the bugs have been worked out of that. It is extremely good at predicting next tokens. So I'm going to take all of that between the pink and the green there and just lump that into this box here where it says next token probability distribution predictor. But I'm going to leave out of that box this block called the sampler. You see the purple one at the top? It's an extremely important piece of the puzzle. So we have a $1 billion machine that works extremely well. And we've got a 5-cent thing, a little random number generator, that is doing its job. But there's this juxtaposition between this $1 billion thing and this cheap little random number generator that turns out to be necessary for the thing to work. So the key pieces are the next word predictor, a sampler, a random number generator, and then the auto-regressor, which is its autocomplete running over and over again on itself. So now we have a simplified form, but accurate, about what a large language model is. I'm going to give you a little picture that will help to give you the juxtaposition between the $1 billion machine and the 5-cent sampler. Here is a little picture of the $1 billion machine with 145 billion parameters. The output of that $1 billion machine is a list of likely next words and a list of what their probabilities are. It looks like a pie chart. So if I ask, why is the sky blue? What the big $1 billion machine will say is, well, the next token might be a new line because we're typing it in and it's not going to put the first character of the answer right next to the question mark. It's going to put it on a new line. After that, the next most likely word is the word the. If you ask, why is the sky blue? It will likely answer, the sky is blue because, and so the is the first thing it does. There's other possible words. It might be the word why. Sometimes it'll go Socratic on you. You ask, why is the sky blue? And it'll say, why do birds sing? Why do fish swim? These questions have been asked throughout history by great thinkers. That's why you can get many different possible words as your next token. When they were developing this concept of the large language model, they started with the huge next word predictor. The first thing that you would try here would be say, well, let the $1 billion machine make the decision about what word we will choose. Take the most likely word. Here's the catch, and this is what leads us into the weird problem of the hallucinations. If you let the $1 billion machine pick the next word, you get short, repetitive sequences like this. You ask, why is the sky blue? And it answers, the sky is blue, the sky is blue, the sky is blue, right? A short, repetitive sequence. So they had to add the sampler to introduce some randomness in the selection. You select from the probabilities on that little pie chart, and so now you will see the executive decision maker of this process is in fact a dart-throwing monkey that receives the dartboard from the $1 billion machine, but the dart-throwing monkey makes the executive decision about what the next token will be. It seems crazy that we would do that, but in fact it's necessary. The machine doesn't give you viable outputs if you let the $1 billion machine make the decision. The net result of this is that we have a range of output behaviors that we can get from this large language model that range between repetitive, if you let the $1 billion machine make the decision, to creative and crazy, if you set the temperature knob on the sampler, if you set that really high, and there's a setting in the middle around temperature of 0.8, where it gives pleasing answers. People find that ChatGPT answers their questions well, it writes good stories, but don't use it for filing your law briefs at the Southern District of New York, right? There's some people who found out the hard way, don't use it where facts matter. So this architecture surprised everybody that it could work at all, but it's put us on a little continuum between repetitive and creative. What we want, what is missing here, and the $1 billion opportunity is to have another axis. What we want is a truthfulness axis, not just a repetitiveness and creativeness axis. We need the ability to have it have some source of truth. Right now, all it has is a training set from which it extracts statistics, and it learns about likelihood. The most statistically likely next words, that's what it produces. Likely next words, not necessarily true sentences. So we need a source of truth. How can we get the truth into the system? I'm going to show you my way of attacking that problem, but that's what we're looking for. So we can have another dimension, and we can dial that to make it very literal, quoting facts, or creative and repetitive. There's two new ideas that I'm introducing here. I've actually made a set of 5 different inventions, and these are the first 2 of the inventions. From the standard architecture, I'm going to add 2 new things. You see these new blocks here? There's the deep attribution network, which I'm adding to the architecture, and I'm adding another little arrow coming out of there for hallucination detection and confidence. So basically, the idea behind the deep attribution network is we're going to extend the architecture of the large language model by adding another neural network whose purpose is to refer to and cite and quote the training set. The training set is what I'm defining as the source of truth for the system. And the training set is not used at inference time. You use the training set at training time. And then once you've got it, you've got the weights in the next token probability predictor. You've got those weights, and you never use the training set again. And what I'm saying is you're throwing away information. Carver always said the brain uses all the information in the signal. What I'm saying is we need to use all the information in the training set. We're throwing away information from the training set that we could be using for truthfulness. So that's the key first idea, is we're going to have to add another network, and it is going to somehow allow us to refer into the training set. Here's how. I called it an attribution network. On the left here, we have a standard deep neural network, recognizing handwritten characters. The way that you train it is you put in, here's an example of a scrawled 3 and a label that says it's a 3. And you train it with 60,000 examples. That's the MNIST toy problem. And you learn up all the weights. And now you've built a functional system. It performs the function of classifying in the way that you trained it. But now I'm going to add something new, apparently that no one has noticed in 40 years. To my surprise, I think this is true. I'm going to add another network that gets to look at the same inputs. But instead of performing a functional classification to match the label that we gave it, I'm going to make it predict something that we also have but has never been used. I'm going to make it predict the index back into the training set. Notice that that is a self-supervised thing. We don't need a human labeler. The computer knows it's got 60,000 images, and it knows the order that they're in. So that data is there already. It's just never been used. So we're going to predict something that we already had. And what have we just invented? We've just invented a neural search indexer. It's like inventing the Google of inside the brain. It's the indexer to your memories of where you learned things. That is like the hippocampus. That is the part of the brain. You don't just learn, for example, how to talk. You learn, who did I learn it from? I have a lovely example. This is part of my tribute to Carver, since I can't be here tomorrow. In 1992, in the mountains of Los Gatos, near Carver's home, the treehouse, I learned a new use of a word. It was after I had spent time 3 years at Caltech. I had learned so much from him. We were driving around the mountains of Los Gatos to get to his place as I was about to join Synaptics in 1992. And I was feeling extraordinarily grateful to him that I had learned so much in 3 years that I was about to embark on a career in Silicon Valley where I would continue to learn from him. I asked him, how does one pay back a debt like that when you've learned so much from someone? And he said, Lloyd, that's not the kind of debt that you pay back. It's the kind of debt that you pay forward. I had never heard the word forward in that place before. I'd always heard you pay a debt back. I'd never heard you pay a debt forward. That's an example where my large language model had to adapt. I had to learn a new word. And relevant to the story here, I didn't just learn the new word. That's the adaptation of my large language model. I remember who said it. I remember how I learned it and what was happening when I learned it, where I was, what year it was. Carver was the one who said it. That's what this neural search indexer is doing. You don't just learn the function. You learn the index into the training set. How did I learn it? It's the secondary function. There are some really interesting similarities. This neural search indexer, as simple as it is, it's very similar to the insight that Sergey Brin and Larry Page had in 1998 when they invented Backrub, which turned into PageRank, which turned into Google and is now a $3 trillion company. That was the invention. And the idea behind it was, don't just use the information that's in the documents. You did the crawl, and you also have the information in the links between the documents, and that carries tremendously powerful information, and that gave them an advantage in 1998 over AltaVista and the OpenText and the other search engines of the day. The principle we can extract from that is use all the information from the crawl, and you get an extra advantage. Carver said, the brain uses all the information in the signal, and what I'm saying, use all the information in the training set. This idea has been hiding in plain sight for 40 years. It's been missed by all the giants of the field, Jeff Hinton, Jan LeCun, Yashua Bengio, Jürgen Schmidt-Huber. Carver Mead himself missed it. So did I. We all missed it. And even recently, so John Platt, Ilya Sutskever, Noam Shazir, Demis Hassabis, Sir Demis Hassabis, who recently won the Nobel Prize. Every one of us missed it for 40 years. So the question is, why? Why did we all miss it until now? And I think it's because this is the first time where source attribution and explainability actually had some economic power behind it. We never needed to do source attribution on the handwritten digits, but we do need to do source attribution to be factual in a large language model. So why now? Because it's the first time it mattered. This is just to show you how I tested it. Basically, if you put in these digits, you can have the left part of that diagram calculate, to score them. Yes, that's a 9. Yes, that's a 3. But if it retrieves the best index, it's basically pointing into the training set. And now you can retrieve it. And now look at the little pairs. See how the 9 that's marked there looks like the 9 that was attributed back. It's a neural similarity detector, which is like a search engine. You ask a question to a search engine, goes and finds you the closest document to what you asked for. This goes and finds the closest element in the training set to what you asked for. Look at the 7s. There's some 7s there that have crosses on them. You put in a novel 7, you get a retrieved 7 that looks just like it. This is an example that it works in the simple case of a deep neural network. Now, making it work for a large language model is tremendously harder, right? It took me an afternoon to build and test the simple deep neural net system. But to make it work in a real large language model, it's a hell of a lot more complicated. It took me 3 months to make this work in practice. I had to do surgery on llama.cpp, and it was hard to get the data out of the middle of the large language model. You have to bring out contextualized embedding vectors, and reading that out, well, it's just very difficult to pull the data out of that code that's been optimized for multiprocessors and for GPUs. So getting the data out is really tricky. But if you do, you can get now a large language model that can give citations on a per token basis as it goes. It's the first demonstration of it, and I'll show you in a minute what that looks like in real time as it goes. I gave you the first idea of the deep attribution network. There's another piece of the puzzle, which is the confidence measure, having the system know that it's on shaky ground right now and it's about to step into a hallucination. If you say that, you'll be stuck with it for the rest of the sentence. So there are moments where you have to be very careful about what word you choose. If we have the ability to cite our training data, and we have an ability to measure our confidence and detect that we're about to go into a hallucination, then we have what we need to build a better system that will hallucinate less. Perhaps we can get it over time with development to not hallucinate anymore. Now we take the deep attribution network that I already described, and we can recall the best training token. So now on the two sides here, we've got the sampler that's being chosen by the dart-throwing monkey, which most of the time is pretty good. It's giving valid English sense, but once in a while, it's going to make a clinker and we'll be stuck with it and we'll call it a hallucination. And those are the moments where instead of just saying the most likely word, we want to actually go look up the reference and say the true word. The true word might be very unlikely. I'm going to give you an example where truth and likelihood are diametrically opposed, and that's where the hallucination begins. Here it is. I wrote a book called The Flow of Time and Money. That is a geeky title for a book. If I ask, what books have been written by Lloyd Watts? The true correct answer, non-hallucinating, is the first book by Lloyd Watts was The Flow of Time and Money. However, when I ask Llama 2 that same question, I get crazy wrong answers, but a frequent one that it gives is the first book by Lloyd Watts is The Adventures of Sparky and Friends. Okay, that's a hallucination if there ever was one. I never wrote anything like that. Why would it choose the word adventures? Because there's only one or two web pages on the entire internet that talk about books that I wrote, like my biography has that. But what's the most likely next word when you consider all the documents on the internet? The first book written by anybody was, quote, the next word is probably adventures, because there's probably 10 million pages on the internet to talk about the adventures of Huckleberry Finn. So the most likely word is adventures there, but that's not the true. So the difference between true and most likely, if we want to ever get out of that, we have to break the paradigm of choosing the most likely thing at the right moment and choose the true thing. And the only way to do that is to have access to the truth, which is encoded in the training set. It's been thrown away all this time, and I'm proposing that we remember it. Use all the information in the training set. If we've got this choice now between the reasonable English answer and the true answer, we need to choose between them. We still have the dart-throwing monkey, it's in the sampler, but we have something that can override the dart-throwing monkey. It's an executive selector. And there's a part of the brain that is going to be doing that. We will need to have a knob on that. Just like the temperature knob let us go between creativity and repetitiveness, this switch here needs a knob. We may want to have something for a lawyer that is highly truthful. We want it to always refer to true citations. We also may want to have something where if you want to ask it for write me a children's story for my grandchildren that I can read to them, I don't care about truthfulness, I want creativity. So there's a knob for truthfulness that lets you select between these two branches. And there's a knob for temperature that we've already seen. So now finally, we actually have a way to be able to have the access that we had and that we like. We haven't thrown away the ability to be creative or repetitive, but we've added the ability to be truthful or creative. The brain regions that correspond to these here, for the first time, we're not just building an engineering device that seems to perform in an intelligent way. We're building something that is starting to look a little bit more like a model of the brain, at least in its broad architecture. Those pieces there, they're just born out of engineering necessity to build something that would work. But now I think that the next word predictor is a pretty good model for what's happening in Broca's area. The hippocampus is where you remember your training set and can retrieve it. That's the memory system, and the frontal networks, that's the executive final decision maker, which is not just a little switch. It's a very sophisticated thing that's determining what am I talking about? Who am I talking to? Why do I want to be truthful right now? That's made those frontal networks, and this is a simple model of that. The famous paper from 2017, that was Attention is All You Need. That was the title of that paper. I would say, no, attention is not all you need, and even language is not all you need. To build a truthful and trustworthy system, you also need memory and confidence and judgment. That's what the real brain looks like, and the 3 blocks we've been talking about are on there. Someone asked Carver not too long ago, how long do you think it'll take until we actually reverse engineer the brain? We build the whole thing. Carver's answer was, don't hold your breath. Quick video demos. It's not just talk. I spent a year building this stuff, doing surgery on llama.cpp, and here's what it looks like. For the attribution network, doing citations, and the hallucination detector, detecting the hallucinations. I'll run both. So both are going now. It'll take about 15 seconds to run both. What's the meaning of life on the left, and what books have been written by Lloyd Watts on the right? See on the left, it's producing citations as it goes. It looks just like ChatGPT, except it's producing the citations on the fly as it goes and marking them with footnotes. On the right, you see the light blue, that's marking where it's not certain. And what do you know? Most of the blue is on the titles, where it's totally wrong. Lloyd Watts never wrote The History of the World or the American Political System. Of course not. It's marking uncertainty where hallucinations are actually happening. And the last one, this turns out to be really relevant to some legal cases happening right now. Copyright infringement alleged by New York Times versus OpenAI. Well, there's a way to allocate royalties. If you wanted to pay royalties to the contributors of the crawl of the data, you can actually do that using the citation technology too. And there's what the royalties look like.